The main task for today is implement proper functions, proper call and read hardware instructions. So far, I've been using multiple instructions to emulate the behavior of call and read, but I have been convinced that it is a good idea to add actual instructions, as in wires, inside the architecture to handle call and read as their own separate instructions. Now, I'm pretty sure this is a fairly open-ended task, similar to the level where we were asked to add RAM, or this is not RAM, to the architecture. There's multiple ways this can be implemented, I'm pretty sure. And the real difficulty is figuring out which way is going to be the best way, the cleanest way, the most optimal way to do this. I actually believe my RAM video is one of the worst I did for Turing Complete, because it's just pretty much an hour of me agonizing about a single design choice. I'm not sure how I'm going to handle this one, but yeah, this is also a bit daunting for me. I'm scared of making changes myself when there's multiple options and none of them are clearly superior. But still, it has to be done, and I've given it some thought, and I think the most important part is not how I'm going to implement it. It's not about how I'm going to wire things, or where I'm going to put new components, new gates or whatever. But really the big question, I think, is going to be how I categorize the instruction itself. So over here, this is pretty much one of my instruction readers. This is my yellow is my instruction line, or what's it called? Opcode, I think, right? Oops. Opcode, I'm pretty sure it's going to be called. Let's check. Well, if I can. Yeah, opcode, the part of the instruction that determines which operation. Maybe memory address. No, still, I think it's the opcode. Yeah, so the question is, what opcode is going to be a call and a read? And of the two, I actually think call is the really important one, and read I might not even implement at all, might not even make it separate, because if we take a look, well, actually I didn't need to go out. If we take a look, my read is already a single instruction. It's already, I just pop from stack. That's all I do. So I could just, do something like const read is mob, and then I know that I have read stack IAR. That's all. So this is literally just notation, and in fact, this is not necessary. A compiler could compile read into mov stack AR, which, sorry, little distraction. Yeah, so like I said, the more important part, I'm pretty sure, is going to be the call instruction, and that is because there's multiple semi-interesting things related to call. So first of all, my instruction is 4 bytes, right? I have 4 bytes. I have 4 of these. And when I call, really, the interesting part is the call itself and the function that I call, which is going to be this line. And I still have 2 free lines which are completely unused. They would be the 2 source addresses for a regular operation. And it's not entirely clear to me if I should just ignore them, or if I should try to make use of them for some extra functionality. And overall, if I were to add a completely separate call instruction group and not make it part of something else, if I don't do anything about these, then all of that instruction space is going to be wasted, pretty much. So, you know, 255 of these times 255 of these combinations of inputs are going to be exactly the same. And I am very greedy about my instructions. I do not want to use my instruction space if I can help it at all. I want to avoid using instruction space. So yeah, there's going to be a couple ways this can be done. Going to be a couple ways I can implement calls, and I'm going to talk about them. But since we're talking about instructions, I think it will be useful to first do an unrelated change to instruction space, which I think still needs to happen regardless, but my choice there will change how I think about calls. So I think it would make sense to do that first. And that is a change to the ALU. So last time we were implementing an algorithm which made use of mod. And what we found out is that we ran out of instruction space in the ALU. So we have these 8, which there's actually 8. Doesn't matter. There's 8 instructions. There's add, sub, and or not XOR mul. And then I need a div and a mod, and I ran out of space, and all I did is I just hardwired my div to be a mod instead, or vice versa, my mod to be counted as a div. So I am pretty sure that at this point, I want to expand my instruction space for the ALU. And this seems like a fairly straightforward task. Right now, my opcode is encoded with these 3 bits, right? This is what gives me the 8 options. And what I want to do is I want to expand this to 4 bits, which will mean 16 instructions, which will give me the space necessary for the mod, as well as any other operations I might want to add in the future. So I think I will do that first. I will do that right now. I expect this to be a fairly trivial change. I just replace this decoder with a 4-bit decoder, and then it's all the same. So I'll do that, and I'll be right back. Something along these lines. So yeah, all I did is I just added a 4 decoder, which, by the way, I made a custom decoder just to shift its, you know, decoder part, this thing, the blue thing. Normally it would be over here, but that would make for a very weird shape in the component, right? If we have something over here, it puts a couple of squares all the way to the right, and I didn't want that. So yeah, this is just that thing shifted to the left, and it's not flipped or anything. I decided that flipping it would be too confusing. So yeah. So now our instruction space is expanded, and I've already wired in, a specialized mod operation, or a dedicated mod operation. So now what we know is that this wire 8 on the opcode is at least used in the ALU, and this means it at least cannot be a mode designating. It cannot mode designating bit. It cannot. I don't know the terminology for this. It cannot be resolved at a higher level and have a meaning above the meaning of something in the ALU. I don't know how much sense this makes, but yeah, that's about it. No, that's actually not the end of what I wanted to do with the ALU. I've stared at this for a while. Well, not a while, but for a few moments. And just looking at these operations, first of all, I don't really need all these logical connectives? That's like the first thing we learned in this game ever, is the fact that you don't need all the logical gates, you only need an AND. And I can create an AND, I can create an OR, and NOT, and an XOR with just a single NAND. So, I mean, honestly, hypothetically, I could just plop a NAND. Where's my NAND? Yeah, I could just plop an 8-bit NAND in here somewhere and get rid of all these. And then if I want to do one of them, then I would just emulate them in multiple ticks. But of course, I don't really need to save this much on this, and it is useful to have an AND and an OR, and overall I think these 4 gates are the most commonly used ones, right? There's actually a bunch more. There's like XNOR, NOR, you know, these are very weird gates, which I don't think I've ever used an XNOR. But yeah, they're not in here, and the ones that are in here are the common ones. But still, having thought about an AND, I think I'm going to make an executive decision, and I'm going to replace this NOT with an AND. Because of course we know that a NOT is exactly an AND wired to itself. You know, if we pipe the same output into both inputs of the NAND, they are the same thing. So now, right, this is a NOT. So in order to emulate a NOT, a NAND is sufficient. So if I plop a NAND into here, I will not lose anything because I can still get a NOT in a single tick if I just pipe the same operand into NAND. And it's not going to be more expensive in terms of gate score, and yet I gain the possibility to perform an actual NAND on 2 inputs as opposed to a stupid NOT. So I think that's going to be a fairly safe bet, and yeah, I'm just going to do that right now. Should be a very simple change. Give me an 8-bit NAND, like so, and like so. Although my programs that we're using are not might be broken now, but that's another story. I will need to go over them and change them, fix them. So yeah, now we have a NAND. Let's get out. This is not going to be the right ALU. Yes, I saved my old ALU to an archive, so let's plop a new one in here. Same shape, thankfully. And let's also update my NOT. Let's rename the NOT into a NAND. So now this is a NAND. Oh, and also I need to add... I already have a div, where's my div? My div is a 7, so now I will have a mod, which will be an 8. Save. Perfect. So now I have a div and a mod in my ALU. I also have a NAND, and I know that these 4 bits are now used inside the ALU. Okay, so that's that. Now the next thing I'm going to turn my attention to is, I think, going to be the ACALL. And yeah, there's still a couple of changes I want to do here as well. Although they will break more things, but again, I intend to make an executive decision here, just like I did with an AND. So I have all these conditions, EQ and EQ, less than, less equals, greater than, greater equals. But I am actually strongly inclined toward removing unsigned greater than and unsigned greater equals from the conditional block altogether. Now, I don't think that's going to necessarily save me much. Of course, it saves me a couple of gate scores, and it frees up 2 operations. But there aren't any operations I want to add to this. I can't really think of any Boolean operators on integers other than these ones, eq and eq less than less equals. But the thing with greater than is the fact that I really, really don't need it because I already have a less than. And of course, a less than b or a greater than b is exactly the same as b greater than or b less than a. Right, I just need to flip these things, flip the operands in it. So a is less than b if and only if b is greater than a, right? So if I have greater ba, then I can absolutely equivalently replace it with less than ab, right? The same goes for greater equals, less equals, right? And this is a completely trivial change, which can really be done by a compiler. So I already have a couple of, what's it called, convenience features in the assembly editor, such as these consts, as well as labels, right? So it does some very basic pre-processing of my assembly code in order to turn it into actual machine code. And this replacement of less than and greater than is as simple as label and const. All you need to do is whenever I write unsigned greater than AB, you just need to compile it into unsigned less than BA, right? Now it won't, of course it won't actually compile it, but I can be my own compiler and I can get rid of all the greater thans in my programs and I can just make do with less than. So I think I will remove this for now. I might eventually decide that I want them, but yeah, for now, gone. They are gone from my instruction set. Let me wire this neatly. Something along these lines. This is a controversial change. I'm not necessarily happy with it, especially considering the fact that I don't have a compiler the way I want, the way I just described. But still, at least for now, I'm gonna make it. We'll see if it comes back to bite me. And yeah, I think I might try to go over all of my old programs. I won't do that on camera, but I'll go over all of my programs and do fixes for less than versus greater than. And actually, side note, I myself am kind of used to always using less than and less equals in kind of programming because, well, because of a very similar consideration. What I generally do in my life is proofs, computer-assisted proofs, and it is often annoying to deal with situations where you have both greater than and less than for different values in your proof, and it's much easier to deal with a situation where you always have less than, because they you can apply transitive properties to them, because if A is less than B and B is less than C, then you know that A is less than C. Well, if you have less than and greater than, you're gonna have problems combining them. It's just a minor thing, weird comment I decided to add for some reason. So yeah, now we only have less than and less equals. And that finally brings me back to the actual question at hand. I need to add call and read as instructions. So now there's multiple ways to do that. And I think what I'm gonna do is I'm gonna go over all the ways I can see for how this can be implemented, talk about what I see as their pros and cons, and yeah, hopefully decide on one. So the first obvious option is we know that these three are used for immediate values. These 4 bits are used for, what's it called? Opcodes. You're forgetting the word opcode. But bit 16, or bit 5, whatever you want to call it, is still unused. This thing is completely unused in my architecture. It is not wired to anything anywhere. Which means that one way I could do this is I could designate an entire new mode of operation in my whole architecture, in the entire computer, which will be designated by bit 16. And if we see bit 16, then everything changes and everything behaves in a different way. And one of those things that might be done with bit 16 could be a jump. So that's one way. I think I'm gonna write it down. This is with the intention of possibly making tables of pros and cons for each option, but we'll see. So that's one way. The other way I can see this can be done, or actually both of them, I see 2 more ways. They're both going to be in ACALL, and they have to do with the fact that we can notice that any call or ret, either of the two, are actually essentially jumps, right? So this is an unconditional jump to a function. And then the function is also effectively a jump, except it's implemented as a mov, but it is a jump in the sense that we are overwriting the IAR with a value. Yeah, no jumps. This cannot be implemented as jump because I need to read the value, and jumps are always to hard-coded locations. So this is slightly interesting jump. But still, we notice that they're both jumps, and since they're both jumps, something I could potentially do is I could go into, I could go into a cond, and in here I could do multiple things. So first of all, I do have 2 free, at least 2, having just removed 2 of these. I already have 4, but still I had 2 free instructions, free opcodes, this one and this one. And I could say that this is call, for example, and this is ret. And, you know, whatever it takes, I think I could wire it up. I could make these 2 wires do me a call and a ret. So that's another way. Let me write it down. Right? A cond call ret as opcodes. This is another option. But this is not the only one to do with a cond. There's one more way I could implement this. It's also going to be inside a cond, and this is kind of a combination of a couple of things. So we've already implemented the ALU to use 4 bits here. And while this does not, I'm pretty sure it does not necessarily mean that this 4th bit is now completely free to use as part of the opcode in the cond. I could use it. I definitely know that it's not, like I mentioned earlier, I definitely know that it's not designating a new top-level mode. So inside of a cond, it might as well have its own special meaning. Which means I could expand this entire thing to a 16-bit decoder, right? That would be, come on. That would, sorry. Where's my... Oh no. Okay, go away. 16-bit decoder. Base 1 bit. For deck. This one. And yeah, I could do this. But now that I've done this, I know that I have my EQ, my NEQ, ULT, ULE. So they are 4 things. This is what's taken. And again, let's just be charitable. Let's imagine I didn't remove these 2. Still, we would have 6 taken up here. And like I've already mentioned, I don't really see many more conditional or, you know, basic integer to Boolean expressions, you know, functions of the type, in imperative terms, this would be bool, CMP, some kind of compare of int x, int y, right? It's gonna be C style, I think. I don't see many other functions CMP other than EQ, NEQ, ULT, ULE that I might ever want to add into here, right? I really cannot tell what I'm going to add in here. Actually, let me give this a few minutes of thought and try to come up with something good. Well, okay, having given it some thought, I think I may have an idea for what else I might want in here. And even though they're integers, of course we know that, at least in C, I'm not sure if that has to do with how the actual hardware architecture is implemented under the hood, but still, at least in C, integers are used as booleans effectively. And for example, I could have bool and int x, int y, where x equals true by definition, I don't know, if x is not 0, I believe, right? Yeah. So, and this would be a Boolean connective, and then I would want this to be non-zero as well, right? So I would want, wait, how would I even? Yeah, I would want an actual non-zero check on both things, and then I would want a 1-bit AND, right? As well as a 1-bit OR, as well as a 1-bit everything. So that's a possibility of something I might want to use, and that would probably put me over the line. Although, let's see. So now my reduction does come into play. I have 4, and I still have 4 free. These ones. So just to tell you, okay, the idea I'm actually working on is something I could do is I could implement a thing one might call a, well, sorry for the terminology, but call if connective. So instead of just a call being just an unconditional jump, which right now a call is an unconditional jump, I could add a free condition into here. And that would be nice in that it would not waste these things. It would not waste the operands. Custom component account has changed. Yeah, whatever. Where's my... Oh no, it's gone. Oh no. Give me a cont. Yeah. So I could implement a call if such that all these are still there. So all these checks are still there, except I could be in non-call mode, which would be the first half of my decoder. And this would just be a regular jump. While in this case, in the other half of my decoder, these would be the same comparisons, except they would actually call and not simply jump. And they are different things. Simply jumping and calling are very different things, I'm pretty sure. So this is what I'm thinking about. And the key important thing for this is I cannot have more basic gates, more basic comparisons than half of my decoder. So if I need a ninth here, then my entire call idea falls apart because I will not be able to have it separately. So let me give some thought to what these might be in terms of and, or, and whatever, as well as maybe something else. And I'll be back. Well, I think these four, just to say the exact same way we have them in the ALU, would be okay. And that would be sufficient for me. That's more than enough, honestly. So an AND, again, I can use an AND to imitate a NOT. And the behavior of them is C-style, in that if the number is 0, then we treat it as a false. While if the number is non-zero, we treat it as a true. So yeah, I would have something like, yeah, I would have a comparison to 0 here. Yeah, no, I would need two comparisons to 0, so compare this to 0, compare this to 0. And then those comparisons would be piped through these, and that would be the output of my condition. And I cannot see anything else, and actually I've looked up the set of C operators, and C does not have any more operators than this. It has bitwise stuff, but I already have bitwise stuff in my ALU. So this seems like a fairly reasonable set. So yeah, and of course EQ, NEQ, ULT, ULE stays. And then again, I can have my bit 8 designate whether I'm jumping or not jumping, or whether I'm calling or not calling. And this would be, but this only accommodates the call. It does not accommodate the ret. Because I have no space left for the ret, pretty much. But like I said, I already have an instruction that is a ret. I have the mov from stack to something, which to me sounds fine, I think. Yeah, the really problematic part, again, to reiterate for the 100th time, is the call, which is two operations. We push the return address to stack. The what's it called? Jump back? No, I forget. And then we actually jump to the function, while the ret is still a single instruction. And this is just, again, a matter of compiling a ret instruction to this, right? So something like compile ret. Wow. Compile is a keyword. Wow. Hello. Actually, no, it isn't. Yeah, it's not. Okay. So yeah, something like compile ret equals mov stack IAR. I could say that these are strings. Wow. This also has highlighting for strings, even though there's no such thing as a string in my architecture. So this to me, this looks the most interesting, because I might as well, like I said, I might as well use the 8th bit. I don't have any other use for it. So I have no reason to save on instructions. And the only difference between, so where's my, yeah, so this third option here is also in a cond. Call ret as cond modes, right? So these are basic opcodes. That they would use two things here, this and this. Well, this would be modes. And the only difference between these two is, well, there's multiple differences, but the only difference in cost is the fact that I, instead of using 2 of these, I use 8 of them, but for it, I get ifs on my calls, so I can conditionally call in a single tick, instead of implementing a condition and jumping over my call with a jump. And since I don't have any use for the other bits, I think I might as well go with this. Okay, let me think about this for a moment, and if I decide on this, then we'll proceed with the implementation. Yeah, I've given it some thought, and I think this is what I'm going to go with. So we can kind of pair them up like this. Of the 2 options, either... Come on. Sometimes it's such a pain to work with this whiteboard. So we can pair them up like this. Of these 2 options, either implement a new top-level mode or implement the new thing inside of ACALL. I would definitely go with this one, because I do not want to add any new top-level modes if I can help it. If something can be done at a more local level, if something can be done as an instance of something else, that's definitely better. This is how you preserve, what's it called? Compositionality? Modularity? Whatever you want to call it. I don't know. Whatever it's called. I think compositionality. So yeah, I would want to go with this. And as I've already explained, of these 2, I would rather go with this than this, because I have no reason to go with this. This is just a more powerful implementation. Seems strictly stronger. So yeah, I think that should be a fairly simple change, actually. This should be fairly simple to implement. I won't actually need the 4-bit decoder. I'll just use this thing to decide. But something else I wanted to point out again, just go back to and clarify. When I was talking about compile here, I think I wasn't... I mean, it was probably clear, but I wasn't expressing it in the correct terms. Of course, compiling is not a trivial task, and just saying that compile ret equals mov stack IAR is not exactly the statement I wanted to make. The exact statement I wanted to make is that this is a absolutely trivial, context-free syntactic substitution. So this is what would be, for example, done with what could be done with a very basic C-style preprocessor, right? We could define ret this stuff. I actually don't know exactly how defines work. Do I need a string here or what? But yeah, you wouldn't need to do any reasoning here at all. You wouldn't need to look at anything. You could just do this with a grep. So yeah, and that's actually, I think that could be a very nice feature to add. This is another feature request I would have for the assembly editor. We can define our own constants, but how about something more powerful? Well, actually, constants are essentially these syntactic substitutions, except constants only substitute 1 byte for 1 byte. And it would be nice to be able to define multi-byte constants, as I've already said. So it would be nice to say that red is these 4 bytes. I think actually it was this exact level when I first complained about this. So yeah, that would be very cool. And actually, also one more thing, let me look it up. All the way back, around part 18, I still remember Yotanida mentioning custom ASM. So looks like this is it. This is its GitHub. Looks like it's a thing where you can define your own instruction set in a much more flexible way. So it looks like this, for example. Yeah, this looks like rule def, the definition of rules. This is how it's to be compiled, and then this is the program, and it compiles to this assembly, which wouldn't fit Turing Complete, of course, but it's interesting, and I wonder if maybe it has options to compile to something Turing Complete compatible, and well, even if it doesn't, still, it's an interesting idea, and I could even consider writing something very simple on my own, just writing a basic assembly compiler to compile into, well, I mean, I would want it to be customizable, so I would want to be able to define custom rule sets, but yeah, something to handle these basic things I have been complaining about, like multi-byte constants and actually multi-instruction constants as well. Yodanido also mentions them. Instructions in the assembly language that actually turn into multiple real instructions in the binary. So this is an interesting idea I might look into. Written in Rust and assembly. What? Oh no, they must be examples, right? Or tests. You wouldn't write this thing in assembly, I don't think. Yeah. But, okay, back to the question at hand. We're gonna be implementing jumps as a cond mode of its own. So I think the first thing I want to do is, I think I first want to implement these, just because, well, I decided I want them, so I might as well implement them. I think this should be fairly simple. I check for equality to 0, and then I use these to connect, and then I have a bunch more options. Right? Something along these lines. I'll figure this out, and I'll be back with that. So this is an interesting thing. I implemented an equal 0. We've seen this a million times. So I can check if one of them is equal to 0. I can also add the other one, so I could check like this. And then this would be completely trivial. But I wonder if I could actually try to make use of the already existing comparison over here to save on some gates in the EQ0. So that I'm not sure that would be neat, but it is an interesting question, is it not? So for example, if I know that this guy is equal to 0, and then I know that they are equal, this is the equal line. If I know that they're equal and this guy is 0, then yeah, I can put an AND here. Then I effectively know that they are both 0. And if they're both 0, I can resolve these without even doing anything. I might need some knots here and there, but... Well, actually, if I need knots, then that kind of defeats the purpose. It still saves on this. So that's one way, but that's not all, because if this guy is equal to 0, and this one isn't, then... Yeah, that will be... That's a question. I'm gonna give this some thought as well. We'll see. Nah, I don't think it's possible without checking either one being equal to 0, because if I only check one, then I will never be able to infer if this one isn't equal to 0 and I'm only checking this. I will never be able to know if this is 0 or not, no matter how I compare them. So yeah, I will want both of these lines, and then this becomes completely trivial. So I'll wire this up. So this is now my new highly advanced conditional block. A cond. I'm not gonna rename it to that, of course. So yeah, this is just the basic operations added, and before I forget, I'm gonna go here, and I'm gonna update all these. Done. Call them B and for boolean, boolean and boolean and boolean, or B XOR. So now all of the basic conditions. Oh, let's plop down the actual ALU or ACOND. Now all the basic opcodes are taken. We'll see if I actually need them. I can't change it, of course, in the future. But now comes the next question. Given this, how do I implement bit 8 as a call? I think this should also be fairly simple, and the real question is, where do I implement it now? Because the jump itself, so a call is 2 instructions, and this part I still literally have covered. Since I am inside the jump, and well, I am thinking of jump, this still happens, and it happens just fine. With a call to function, I can use some different kind of jump. So jump if boolean XOR, for example. This now exists. I can do this now, and it works for functions just the way it did before. But the idea is, I would add bit 16 something, I don't know how I would call it, to this instruction. So, well, I guess I would call it a call. And then it would need to perform this for free. It would need to perform this in the architecture. So actually, I'm not even sure if I need to do it inside the ACOND, if I need to make this decision inside the ACOND, because I could alternatively wire it out here, you know, get this 8, and then if these both hold, right, I still need the ACOND to hold, and I still need all the infrastructure with ACOND, so I would need to, you know, bring out of it, then I would have an AND, and we would say if both of these hold, then go all the way down here and push something to stack. Wherever the stack is. This is the stack, I think. Yeah. So, and then this gets pushed, something gets pushed to stack here. Now, I'm not sure. I could, of course, alternatively do it inside of here. I could have this, and then I would have the AND also inside. And yeah, we would be ending this with this. And then we would have another output, and it would be the same outside. And I'm not sure which way I want to do it. I'm actually inclined to doing it outside, because this has nothing to do with, well, other than the fact that it is an AND. Okay, give me another moment. No, I think I'm putting it into ACOND. The reason being, the meaning of this thing is local. It means different things in ALU and ACOND. And if I were to do something outside, that would kind of suggest a global meaning and architecture-wide thing. So yeah, what I'm going to do is I'm going to add another output to the ACOND. This should be very simple, actually. What I want is a switched output, 1-bit switched output. Which just about fits here. I actually have a lot of space for it, but in case you haven't noticed, I've been aligning all of my inputs and outputs to corners. So that's one thing I do. Yeah, and all this is really is we want bit 8. Oh no, it doesn't wire nicely. But we only want it when we are in fact jumping. So that's it. Let me try to wire this. Nope, it doesn't wire any better than this. So yeah, now we'll have another pin on the output. Why on earth are you on? No, it's not on. Okay. So yeah, and this guy we can take, and I'm gonna want to bring it. I hate this. Oh, I hate this so much. Yeah, I knew this would happen, and I knew this would be necessary, but oof, I really don't like this wire. It breaks all the things I have strived for so far. It's so bad. Yeah, I will need it to be all the way down at the stack level, and then what I'm going to do is and I hate this. I hate this so much. There's no way you can implement this without some wire going down to the stack. Right? Surely not. Surely not. Maybe a different output location? No, that's not possible. I'm already in immediate output mode. Maybe different input location. I'm in denial. Give me a moment to process. Okay, I think I'm all the way to acceptance now. My grief is accepted. So what I will want to have now is I will want a thing in the stack, I think. Do I? So again, I'm thinking I will definitely want something. I could do it entirely outside. So I think something I could do, for example, is I could put an OR here, because I know that when I'm doing a jump, this decoder will be off, right? It's off because I am in immediate output mode. So this decoder is off and nothing is happening here. Wait. I'm back to denial. How about... Oh, this would be great. Look at this. Look at this. Check this out. You're not broken. Leave me alone. I said, leave me alone. This pin is off. What's wrong? Circular dependency. Circular dependency... Where? Unacceptable. Unacceptable. Why? Okay, give me a moment here. Oh, right. My conditional jump can happen based on what's on stack. I don't know if that's still not a circular dependency though, right? Because stack... Yeah, the output of the stack is necessarily delayed through RAM. So this is actually fine. So I think I might just plop a bidirectional pin here. And if I want to... Yeah. If I want to... Wait. No, that's not good. Wait a minute. So the problem is now... Oh, the way my stack is implemented, if I'm popping and pushing at the same time, I will be replacing my... Yeah, no, but that's fine. I'm replacing. I told it to pop. So it's fine. I can pop something from here, do a comparison, and then push the stack, and we're fine. Yeah, so I think it's fine, and I think I can just plop a bidirectional pin here. Value, yeah, I've been using this. Let's get a bidirectional pin in. This is gonna be value still. Like so, back. Hopefully no more circular dependency. Still a circular dependency. Why? That's not good. Where is... Oh, there's also a circular dependency in a cond as well, right? No, but it's... Again, it must be okay because stack delays it. I don't understand. Yeah, this, I don't care what's inside here. The important part is stack will necessarily delay your... Yeah, what? It's impossible to get the pushed thing from RAM in one tick, right? If I tell RAM to push something and pop at the same time, or, well, to save something and load at the same time, RAM is going to load what was saved and not what is being saved, right? I can check it very easily, right? So I can do load. I am both loading and saving at the same time. And let's say I'm loading some, I'm saving some constant. Address is going to be 0, that's fine. I am saving a constant, whatever, 48. And I'm loading it. I expect to load a 0. Yeah, I'm loading a 0. But now if I press next, 48. Why am I still loading a 0? That's weird. Still loading a 0. Okay, now I'm loading a 48. Oh, of course, yes, that's fine. Wait, is it? Wait, what? No, I shouldn't be loading a 0 at this point. 48 is saved. I'm loading it. I don't understand. I mean, this is definitely good for this part, but now I'm confused by RAM itself. Again, it didn't update. Okay, now it did. It doesn't update after the first tick. This output is still 0. I don't... Okay, no, that's... I'm not gonna go into that for now. Still, this output is necessarily delayed. We've just learned that. So why, oh why, are you a circular dependency? Okay, give me a moment. Okay, so substituting this entire component in place did not help the circular dependency. It's still there. Looks kind of different, actually. For some reason. What even? Short circuit ALU? With the ALU now. Okay, I may have wired it wrong or something. Yeah, I did wire it wrong, but the main problem is still there. We still have a circular dependency with ACALL, even if I substitute stack in place. So it looks like there is a problem here, and it looks like RAM is in fact not guarding against circular dependency. So I guess let me check RAM itself. Just isolate and issue a circular RAM thing. Be right back. I think I see an issue. I'm not entirely sure yet, but while it is okay, which is completely unconnected, while it is okay to, while the RAM does act as a delay on the value being saved, there is still a problem with the address, because the address from which we load influences the value loaded on the same tick. This is necessarily true. So inside of here, there is a direct path from this to this without any delay. That is definitely the case. And that is where we get our short circuit. So the short circuit is with the address. But I'm still not sure exactly what this means and where this comes from and if this is in fact an issue. So I'll be right back once I figure that out. I just realized this is not a solution to the problem, but I just realized I had this thing wired wrong. What I used to have was completely backwards. I was enabling this guy with this, and then passing through the signal from 32. Or actually, sorry, from 16 or from 8 it was. But now I'm realizing that really what I want is I want my... so this is actually... Yeah, this is called call. I don't know why it's called 1-bit switch. This is call. I want this guy enabled when I am both in comparison mode. So this is conditional mode, bit 32. And I am, in fact... Oh, this is wrong again. Man, this is kind of a pain to wire. Because this needs to go up. Yeah. So comparison mode is 32, which means this will output. And then if I am both in comparison mode and I am in call mode, so bit 8, then I need to enable this guy. And whether or not this guy actually happens is defined by whether or not the operation is successful, which this kind of seems redundant, honestly. I have 2 bits which are the same input, you know, the same value, this one, and this one is only enabled when this one is enabled. Although sometimes it might not be enabled even though this guy is... I don't know. I think it is correct. But I still haven't figured out the short circuit issue, so let me continue with this. I'm trying to build a specialized basic thing which just assumes I'm constantly popping from RAM. It's always piped into ACALL, and I want to figure out why this would be a short circuit. Okay, so the issue looks fairly clear in this setup, but I don't think it is anything fundamental still. I still think this should be fixable, and it's probably to do with my implementation of the stack, and I think I just want a different logic for the stack again. Yet again, this is going to be the 3rd remake of my stack. So what's happening here is these are my pop. These two, the OR of these two, defines whether I'm popping or not. And the only thing I use the pop value, whether I'm popping, is in order to decide whether I change the value in the register, and that is, you know, through this XOR. But interestingly enough, whether I am popping or not currently does not influence the actual address at all. You can see that these wires completely miss this entire part, which decides the address. So my address is currently exclusively decided by whether or not I am pushing, right? So this green line is my push line, and based on it, I decide the address. But what's currently kind of happening is I know that I am popping for sure, and I'm not yet certain whether I am pushing. So of course, when I want to decide the address of what I'm popping based on the output of a cond, based on whether I'm pushing, that is a problem, because in order to decide whether I'm pushing, I need the ACOND to resolve, and in order to resolve ACOND, I need to know what the values in it are, and in order to know the values, I need to know the address, and in order to know the address, I need to know the result of ACOND. But I think this is not a major issue, and I think I can have this behavior quite easily, at least for the moment. Let's try a quick wiring. If instead of deciding on push itself, I simply decide based on not pop. So push and not pop are, of course, the same thing. Yeah. See, and this works. And I think this is equivalent. I think this is equivalent so far as... Actually, I don't know. Is this even... This might not be correct. I think I may have had it wired this way before, and it was bad in another way. It was bad in how it treated pushing and popping at the same in one tick. But you can see that this at least this clearly definitely resolves the circular dependency. But this is a weird issue. This is a weird question, and I need to be really careful here with what I do. I might also perhaps I might want to use multiple decoders. Like I might want to do another decoder, one decoder for push, one decoder for pop, and then the output is decided based on the combination of the two as opposed to just on one. That might be another good thing. So yeah, let me give this some thought and I'll be back. Okay. So I spelled it out. I spelled it out using a redundant set of gates, which should be reducible. But I spelled out exactly what I want my behavior to be. And connected into the ACALL, this is no longer causing a circular dependency, and yet I think this is still working correctly. So let me go into, I actually did it in a new component I called whatever, doesn't matter. So what I do is, instead of having this complicated switchboard, I literally spell everything out. So I know that this, the green wire, is the fact that I am pushing. The red wire is the fact that I am popping. So then there's multiple options. Either I am pushing and not popping, so it's this end, which means I am just popping, so it's green. Or another option is I am popping and not pushing, so it's this one, this is the red wire. Or the final option, I am both pushing and popping at the same time. This will be a special case. So now I have this board of 4 switches, and for them I need to make decisions. Now the first 2 switches are deciding whether I'm incrementing or decrementing. And of course what needs to happen is, if I am pushing, then I increment. See, I messed up the wires here, I think. Yeah. Like so. If I am pushing, then I increment. If I am popping, then I decrement. Okay, now I'm scared that I messed up more wires because green and red are kind of confusing to me. Yeah, so again, if I am only popping, then I must decrement my address. If I'm only pushing, then I must increment my address. That's what's happening here, and we have this piped into the base register. But now then, there's the next choice I need to make, whether or not I am working on the currently saved value, or I'm working on the next saved value. And the important part here is, if I'm pushing and popping at the same time, so this one, then I need to use the saved value. So I am currently pointing at what's been saved. I am pointing at the top of the stack. And that's what I want to use. As well as I also want to use this address if I am only popping. Yeah, so this is correct. And I only want to use the newly calculated address if I am currently only pushing. Yeah, so this is the logic behind it. I think this is correct. and this does work. It doesn't cause a circular dependency. And I think maybe a helpful thing to show here would be if we take a look again at the old one. The problem is this address is influenced by what's currently saved, and when whether I'm popping or not does not actually influence this output at all, the address, right? With this wiring, it doesn't influence it at all. While pushing does influence this wire, right? You can see that it changes. And the same thing happens if they're both on, right? This changes based on whether we're pushing or not. So the address is necessarily decided in this setup by the value of the push pin, as opposed to the value of the pop pin. But really what it is it has to be a combination of the two, I think. And now my task is to try to reduce this to something more manageable, because this is way too much. I think it might be as simple as removing... Oh, I don't know. Okay, give me a moment here. Okay, I reduced all this, and it actually reduced completely. It looked like I didn't need any gates at all, which is a bit worrying to me. But yeah, this does end up using both of these things, and it doesn't assume that they're opposites of each other, which is good. But what I wanna... You know what? Let me just go and test this where I was at the point where I was first adding the stack. So we should have a level called stack. No. Man, I still haven't optimized this. Well, good thing I haven't gone back to this, because I still haven't decided on the actual behavior of the stack. So, yeah, push and pop. Okay. So right here, let me try to plop in a my new stack, the one I called stack gesture call. I need to get rid of that bidirectional pin, by the way. Oh no, it just causes a circular dependency by itself. Wait, no, it's... What? It was working just... Oh no. Oh man. How did this work just now? Was it just unconnected? I didn't notice. Did you see it? Was it unconnected? I'm gonna go back and check the footage. I am now very confused, because check this out. This is a circular dependency, right? So this is my current thing. And if we go back to the footage, and I even line it up, this is what I just had. Right, I can switch between the two quickly. They're exactly the same, well, up to the movement of a cond and, you know, a couple of wires. This here was the thing I fixed, but it has no influence. And other than that, they're exactly the same circuit, so far as I can see. Like, the exact same circuit, nothing changes. This changes, this changes. You know, I can try to, come on, do something like this. Oh no, but now I'm gonna need to line it up again. Yeah, lining these things up can be a pain. It's the exact same thing, except now if I connect it, it's a I don't understand. It's connected. You can see that it is connected, and there's a signal flowing here, and it's not an on, definitely. So what else changed? I don't... Are you seeing it? Am I just blind? The ACALL is exactly the same. Eh. Come on. How was it? Something along these lines? I don't know how to. It doesn't matter. Cannot matter. What is happening here? Okay. Oh, yes, I know what's happening. It's these two pins over here. They need to be connected to switches so that it's actually passing the data from the stack to the ACALL. Oh well. Okay, back to the drawing board. I'm still not giving up. I am convinced that this must be solvable. At least it really feels like it. I think if I give priority to the pop operation and don't use push, you know, in the way I explained back over here with the flipping of these bits, I think it should be possible to, if I need to make my stack in such a way that pushing does not influence the address. So actually, yeah, I think I need to change the handling or the semantics, the meaning of the address in such a way that currently what I have is my address is pointing at the last saved thing. And if I'm pushing, I need to increment. While what I want instead is I want to push to the thing that's currently goodness. I want to be pointing at the next location, right? Or whatever. I need to figure this out. Give me a moment. This is so confusing. I've spent so much time on this. This is unexpectedly confusing. Okay, I think this is it. I think this is actually it. This is actually the solution. So what this does is the decision on what the address is completely offloaded onto the or even all the logic, including what's actually saved to the address and what the address on RAM is completely decided by whether we're pushing or popping. That's all, or sorry, whether we're popping or not. So all of this is only connected to this OR. So now this address will only change when I flip the pop pins, right? This address right here only changes when I flip the pop pin, right? Pop pin flipped, address changes. But the flipping of the push pin does not influence the address anymore. And instead, all it does is it changes whether we're actually saving, so this wire, and it also influences whether we're saving the new address. So if we're both pushing and popping, then we're not saving it. And, well, the other way around. So I am pretty sure this should work. Let's test. I am in the push and pop. I have already wired it and there is no longer any. Actually, let me go back and remove these pins again. Bidirectional pin no longer needed. IO input, 8-bit input. So this will be a what are those values? Jeez, what is that value? So this will be, oh yeah, there we go. No more circular dependency. The stack now behaves differently. It has a different meaning on the address, like I explained. I don't think I was very coherent, but you know, there's two ways for it to behave. Level complete, success. So the stack is working. There's two ways for it to behave. Either the address is pointing at the next location to which we're going to push, or it is pointing at the last location from which we're going to pop. And I switched those two, so now it is pointing, I believe, at the next address we're going to push to. So if I enable push, we're going to be pushing to the same address. And that's it. Finally. No short circuit. And we can go back to the... No, to the functions. No. To the functions level. And proceed with implementing the final part of this thing. And I think it might still require me to run a yellow wire down, but we'll see. So the final part of what I need to do, now I know that I can enable my push manually over here, and it's going to be fine. But what I need to change is I need to change the value that is saved. So the value that is saved, I want to be this thing incremented by twice the width. So by 8, this would be this plus 8. Actually, let me... So just a real quick note. I mean, in a perfect world, what I would actually have is I think I would have a 8-bit constant defining the instruction of my the width of my instruction. For example, a 4. And then instead of having this plus 4, I would have a full adder. And I would be adding this, and then I would reuse this 4, just so that I don't have multiple copies of the same magic number 4. And I would add it twice, but in order to save on some score and, you know, wires, I think I will want to implement a plus 8 element. So that I will do right now. That's no problem. There we go. We have a plus 8 component. And so the input to the plus 8 is this thing. Then it goes here. And long story short, I need to decide whether the saved value is actually this, because when I'm calling this is going to be immediated from here as my function label. So the address of the actual function, the instruction address, versus this thing, which is going to be my return to the place where it was called. So what I need to do, at least this will work, is I need to do this, and this mux, yeah, it's the other way around, unfortunately. It is unfortunately the other way around, so I can do something like this, perhaps. Actually, wait, what am I doing? Oh my goodness, these muxes. I don't know what I'm doing. Let me just wire this quickly and then I'll clean it up. So the default of the mux is this pin. That's my output. But then instead of the default, I can override it with this value, except plus 8. Something along these lines. And the decision between which is which happens based on this, I believe. So it is effectively something along these lines. Let me think of how to best actually implement this? Do I want to put this inside the stack? Do I want to maybe put this inside the IAR or inside the stack as well? What can I do about this yellow wire? Let's see. I hate this. I hate this so much. Man. This is pain. I can't even look at this. There's no good way to implement it though. It's just impossible. This +8 and this mux and this wire, they just don't belong anywhere. Right? If I were to put the +8 inside the IAR, that would mean I would need another output and then I would have another wire there. Which, I mean, maybe that would be better. This yellow wire needs to go down here regardless. And well, technically, now that I'm bringing this all the way down there, I don't exactly need this one, strictly speaking, because I could just do an OR on this guy, right? So I would have something like this. That's what I had originally, pretty much, right? So OR this and this, and that would be the value. But nah, I still feel like keeping this and not using an OR. So I think for now that's probably my best bet. I don't like it, but I can't really come up with anything better. And let's try to test it. Hopefully it works. So I now have, yeah, I know I should now have call, and call is bits 38 or 32 and 8, right? So this means bit 32 means I'm jumping, so this is effectively a jump, and 40 means, or 8 means I am calling. So now I have a call, so I don't need an unconditional jump now, and I don't need this anymore. So I can now just directly call F2, and I can also call F1. Yeah, and I don't need this either. Let's try and see, I guess. So F2, yeah, F1, and I keep calling F1. So what's happening here? Yeah, I expect to see registers A and B increasing in unison, in step. It's not working. No. Oh, is it? No, it's kind of working, but it isn't really. Why is it not working? Wait, is this correct? Yeah, I expect, so this increments A, calls F2, F2 increments B, pops, goes back here. Is it 8 that I need to add? Let's see what's happening. So it's clearly it's kind of working, but it's just off somewhere, I think. Oop. Let's see. So I call F, I add 1. I call F2, I add 1. And then I pop. What? Excuse me? Why did I pop F2? Did I? So let's do something like over here. Let's do immediate 1, add 100 to C. So am I gonna get into here is a question. So F2. Yeah. So it looks like it's not +8, but instead +4, which is really weird. That's actually really weird. So let's try +4. I'm pretty sure I had 2 times instruction width. I don't know what's happening there. Okay, where's my plus? Or this would actually be good for me because I can ditch this +4 and I can now add another output out of here, and it would make more sense. So let's try if this works now. It doesn't. Now it doesn't work at all. At least, so it would seem. It seems to reach down here, but B isn't. Oh no, B is increment. Oh yes, I'm just looking at the wrong place. Yeah, it's working. Yes, 57, 58, 59, 60. Yes, it's working. This is correct. Okay, so now I don't need this +4, which is great. And instead, what I can do, I'm happy with this. Instead, what I can do is, let's remove this for now. I can add another output to my IAR. Output, 8-bit. Down here, I guess? I don't like this. What would be a good shape for it? Okay, give me a moment here. Nah, I think this is about optimal. So we have current output and then we have next. So this is good because now I only have one constant for instruction width and it's used for both. So now this remains here. However, this guy can go like that. And also let's add some space. 1, 2, I usually have, I believe. Yeah. So, yeah, this is now a 4. Let's see if... Yeah, this is working. Cool. Cool. All right. If you have any suggestions, and I mean any suggestions at all, please, please, if you know how to remove this yellow wire or fix this, you know, reduce the amount of wires I have out here on the architecture schematic on this one, please let me know. But I think that's gonna be my solution for now. What a mess. But we can proceed to the next. I'm not gonna do this now, but I'm curious just to take a quick peek. We need you to help clean up the basement. Specifically, we want to... Oh, I already recognize this. I think I saw this in the trailer. Yep. Yep, this is gonna be another exercise in recursion. Okay. Well, now we're well equipped with calls. So we can hopefully do better recursion now. Although I expect this to need local variables, which I still haven't learned how to utilize, but I guess we'll learn next time.